Hello, my dear students, and we continue our practical classes. Today it will be practical class number 4, number 5, must be number 6 also, I hope. 3 classes are enough to study this. And the words for you, this time it will be really complex, maybe for you, maybe not, who knows. And good news for you that it will cost you more than previous task you have got from me. What does it mean? Take a look. At the top, you see task number 3, altogether 25 points. You will see during my explanation that here we have the calculations, and some portion of your work will include drawing, not even drawing, something like elementary painting, but of course these paintings supposed to be according to engineering rules. I mean, you need to do it in scale at least. And result supposed to be the what airplane drawing, not like this, of course. What it should be, we will see at the end. And right now, let's start work. What is the work this time? We are going to design airplane. You will have variants. Again, these variants will include some initial information. What is initial information? Above the all, type of the airplane. I think it will be only passenger or cargo. Maybe I will stop even only on passenger. No, preliminary I did the distribution of variants by passenger and cargo airplanes for you. Next, in order to make your life more difficult, you will have different variants of payload. It means amount of passengers for passenger airplane, and the range of airplane. And that's it. Practically nothing else we know about your new airplane. Do you imagine that we are talking to customer, and customer says, I need to transport people or cargo, depends on, to transport them on such distance, in such amount. That's it. You know nothing else. And next we start our design. Step number 1. Step by step, really. Step number 1 for you will be, no, look, some things I have already prepared, but we will try to do it together simultaneously. No, in real, online, let's say. Step number 1 is collecting and analyzing of prototypes. First, we need to analyze statistical data. In our normal life, we may go to library. In library, we will find reference books about different airplanes. No, in case we are located in the room, or we have our library in soft variant, like internet, for instance. In this case, we may use internet for collecting the same information. What does it mean, the same information? Example, you might see it now. Maybe I need to increase the screen. Example, I will show you one example of airplane what I took voluntary, 50 passengers, and ranges around 3,000 kilometers. And what I've been doing first, I asked Google. No, in your case it will be not Google, but some Chinese system, like airplane. Let me to check language. Airplane for 50 passengers. And it starts showing me different photos, different aircraft, and propose me to make more familiar with them by clicking that to another. Of course, some of them are wrong, quite clear. For instance, this little creature, quite clear, it's not for 50 passengers, you might see. No? Some names you know, like Airbus, Boeing, Bombardier, Fokker, Tupolev, Yakovlev, Chinese companies I trust, and so on. So you may ask for some particular name. And checking what you have found, whether it's really correspond to your task. No, in my case, I been talking about 50 passengers. I choose, as you might see, some airplanes. Of course, there are a lot of them. But, as an example, I start working with 5 of them. No, for demonstration of example, it was enough. 3, for instance, not just in average. So I stopped on 3. What I took, A321. Oh, no, it's mistake, because A321 was greater than necessary, and I'm checking together with my notebook and paper also. I took another one, A318, because it was for 100 of not for 100 of passengers, for less passengers. Oh, maybe I'm wrong. Maybe I've been searching for 100 of passengers. Let me to see. Of course, for 100. I should check. I should check myself. Clever woman. Так, for 100 of passengers. I been checking for 100 of passengers, but originally been going to work with 50. So I wrote wrong and have not noticed it after I have been checked everything in these slides. I have not noticed this idiotic mistake. Look, 100 of passengers, and range is around 3,000 kilometers. So Airbus A318, Antonov 148, but it's appears that it's less than necessary. It's around 80 passengers only for. Beta one is Antonov 158. In this meaning, it's for 102 passengers. But I have not found much of information about it. No, what kind of information we need, we will see. And Tupolev 014, the ancient one at all, it's an airplane of 15, 16 years of previous century. You should understand, of course, that the more new airplane, the better. I made it on purpose in order to show you some interesting effects, let's see. And let's start work. What do we need to do? We need, let's jump to the end. We need something like this. We need general drawing of general appearance, general view of the airplane. Each such drawing, as you might see, it's consists of 3 projections, 3 view to the left board, the top view or plan view, so called, and front view. They must be placed exactly in this position, as you might see. Main view, it's a view to the left board, and it's like it's flying to the left or running to the left. Next, at the top place, view from the top of airplane, and on the left place, left view, so call it. It should be the front, the face of the airplane. I took these pictures in internet. Of course, I may show you only something that it does not contain any secrets. So the bad quality of these pictures, it's explaining that I took it in internet and they were very little pictures. There are examples of some diploma projects in our country. And what you see here as text, it's so-called technical specification of airplane. So it comes about its takeoff weight, its capacity, range, practical sailing, flying speed, and another things like this. Well, so as a result, we're supposed to have something like this. But right now, we know only one, practically 2 things we know. The range of flight, the distance it should cover, and the amount of cargo passengers it's supposed to take off. And how to start solving this problem? No, I hope you do remember that in our one of previous classes, we spent the whole class for this. we've been talking about the wrong place I stopped it in these slides. We've been talking about the general appearance of airplane and equation of Можайski. Equation of Можайski or equation of aircraft existence, airplane existence. Well, it's named by Можайski, but developed by another person, really, Bolkhovitinov. There are two portraits here. I do not mean to explain you once again what it comes about. I'm just mean to remind you what it comes about in order you recollect. That is why I'm reminding you about those persons above the wall. Maybe you will recollect this class by explanation about these people, at least. And what was idea of this equation? That all the masses of airplane which finally create its take-off mass or flying mass or take-off mass. These masses consist of, above all, the weight, mass of the structure itself, the weight of equipment, which is specific, let's say, for this airplane, the weight of crew, the weight of engine, the weight of fuel, and the weight of payload itself. What does it mean specific? It means that, for instance, for a passenger airplane, we need armchairs to accommodate people in. We need some toilets, maybe. We need kitchen, depending on how far this airplane fly and how comfortable it's supposed to be. A lot of different equipment, specific equipment for people. Plus to this, we need navigation equipment. Plus to this, we need radio equipment to communicate to the Earth. And another sort of equipment whatsoever they are on board, that we don't know what sort of equipment at all we need and how much it weighs also. So we do not understand what is the list of this equipment and how much it weighs. First. Next. Fuel. How much fuel should we take? Fuel, theoretically, we may calculate amount of fuel, understanding the distance. The far distance, the more fuel we need, quite clear, for the same engine. In case you design airplane for 1,000 of kilometers or for 5,000 of kilometers, the amount of fuel will be different. For the same payload, for the same type of engine, it's another amount of fuel. So it's another takeoff weight of the airplane, seems like. We may calculate it in case we know the type of engine. Do we know the type of engine? No. For instance, we may see the type of engine like turboprop or turbojet, depending on what range of speeds we are going to use, up to 500-600 kilometers per hour, it will be turboprop engine. And if it will be more close to transonic, something like 700 kilometers, 800 kilometers, 900 kilometers per hour, it means that it will be a turbojet engine. Moreover, it will be turbofan engine. And for passenger airplane, and for cargo either. Great. So we may understand the type of engine, but we do not understand the particular model of engine, the thrust we need. Why we do not understand what thrust we need? No, because we don't know the weight of airplane. As we don't know the weight of airplane, we don't able to select the engine. And to understand the weight of airplane, we need to understand the weight of equipment, the weight of structure that has not been designed yet. The weight of passenger payload, it's okay, we understand it. The weight of fuel, and seems like circle is closed, circle of our unawareness, let's say, about initial data, and we're supposed to stop. If not this equation that may help us. This equation proposed to work with so-called relative weights. Relative weights that altogether should give you the value equal to 100%. But relative weights, we also do not understand how to distribute the whole weight, the whole mass, for different submasses, let's say, how to distribute it. That is why we're interested to know statistical data. Let me to find it quickly. Task 3. Here is. Let's switch it off again. And that is why we start with collecting and analyzing of statistical data. Okay, Airbus 318. Airbus 318, it's not Airbus 318. Airbus, it's Antonov. Airbus, no, it's not Airbus again. Okay, just in front of you, Airbus 318. No, thank you. It's proposed me artificial intelligence. And here is must be English version. No, at least in our versions, it was a technical characteristic of it. Oh, and here is it also exists. Out of such data, or you may immediately ask question about something like the speed on runway, for instance, or speed on landing, type of airplane typing, and asking some particular parameters that you need. Watching this, we may select and collect some data we are interested in. What data we are interested in? Let's take it less. Above the all, we are interested to know the weight. I hope you already understood out of my weird explanation about the closed rings that we are moving into, because we don't know neither forces nor masses, nor sizes also. We do not understand how to start. And typically airplane design, it's fulfilled, it's accomplished in some big stages or so-called iterations, approximations, iterations, even in weight designing. Above the all, first we are trying to work with Możайski formula to understand what may be approximately the weight of our airplane. On next stages, you will detailize, in real life, you will detailize the weight each time, already not by approximate formulas, but next understanding approximately the geometrical sizes of airplane, you will be able to determine approximately the loads that acting to the airplane, air loads, weight, and so on, approximately. On next stage, when you already understanding the loads, able to calculate inner structure. After calculating the inner structure, you already know the exact weight of this inner structure because you already calculated in real, in metal, in pieces. And after you know its real weight, you are able to detailize to make more accurate values of loads and check again how structure correspond to the loads that really should act. So it's iteration way, and it takes some months, some years for the group of designers. But originally people start with so-called first iteration, zero iteration of masses, actually it's called M0, and for this zero iteration it's enough to use statistical data. Now after we understand that what we need, why I make this table like this, you see take off weight, it's maximum weight we're working with, it's the whole weight of the airplane, and empty weight, because it's rather difficult to find separately weight of structure and weight of equipment. So I propose you to work with such a characteristic like weight of empty airplane or mass of empty airplane. Usually it's given in internet and given in reference books about airplanes. What does it mean empty? We have empty unequipment airplane, and it will be lighter than it's shown here. And we have empty equipped, so-called airplane. In internet, mostly you see the weight of empty equipped airplane. And next, what you may find on internet with this, the crew, when it comes about passenger airplane. When it comes about cargo airplane, again, either two pilots enough, or it's enough two pilots and let be couple of technicians who are on board and they are in cargo cabin, for instance, responsible for them for watching the cargo cabin during the flight. Of course, if cargo cabin is not pressurized, they will be somewhere in cockpit. But whatsoever, some technicians may be on board either. Next, payload, it's understandable, and weight of fuel, it's usually given immediately in this reference information about the airplanes. Now, let's compare to what I said. Here we might find some weights of airplane that in question, let's say. Of course, it will be a little bit difficult for you because you might find it in different modifications or with different amount of range, for instance. Just take one of them which is more appropriate for you, for your task. Next, my dear people, what about payload, so-called? When it comes about the cargo airplane, it's very simple because it's just given in tons for you. Some way it will be 10 tons, some way it will be 20 tons for one of you, for another of you. What about passenger airplane? How to calculate payload? Because it's usually given, not typically, it's given in amount of passengers. Do you remember what I said about more than once already about so-called standard passenger? Standard passenger is considered like, typically it's considered like 80 kilograms of passenger plus 40 kilograms of passenger luggage. Of course, some passengers, they may took more luggage. In this case, you know that they need to pay more time and so on. Those, let's say, lufts, these little gaps in terms of weight, of course, they exist in real life. But in our first approximation, we will consider that one passenger is 80 plus 40, 120 kilogram. What you see here, 120 kilogram. I took information about A318 with 107 person. Each of them is 120 kilograms, so they are, and they weight next. The same is Antonov 148, 80 person, 120 kilogram. And in another source of information, I've seen payload weight like this. No, we may even check, does it correspond or not? No, not right now, okay. And Tupolev, also you see payload in tons, 9 I have found. And no, I do remember it was for 100 of passenger, maybe 95 or something like this. And weight of fuel, you see the last column. What is next? You will see right now. Finally, consideration about crew. If it's cargo airplane, either you found directly for prototype what is the crew, and crew may be so-called flight crew and technicians crew. And in case of passenger airplane, we have flight crew. Now, typically, practically for all the modern airplanes, flight crew is two people. Two people, it's pilot and co-pilot. Second, pilot, which is something like doubling system. I said it in one of classes that for reliability, for airworthiness of airplane, we are doubling and standbying all the systems, including the pilot. According to the rules of ICAO for civilian and cargo airplanes. This not quite so for military airplanes, but for cargo and for passenger airplanes, for civilian airplanes, for civil airplanes. It's supposed to be like this. So people, two in cockpit, and we have people who are working with passengers. Amount of these people, amount of stewards, it's counted also considering the special norms, let's say. And it's actually depends on the class of airplane, not the purpose of airplane, not the range of airplane, but class of cabin inside of airplane. You know this economy class, business class, and first class. Amount of stewards will be different there. When it's in so-called economy class, it's maybe even for 50 passenger, one steward. When it's in business class, let it be 25, for instance, people served by one steward. And in the first class, no, practically one by one. Not quite like this, of course. These norms we also may find and analyze and use. But what I propose you to do in your first task, simplify it. And let's think that we have, for instance, one steward for 25%. And approximately it corresponds to data that I have found in internet. Here, tuple of 100 for 5%, it's flight crew. It's without stewards. Flight crew was 5% because it's ancient airplane of 50 years of previous century, as I'm already said. There, besides of pilot, co-pilot, we have additionally the one who responsible for navigation, the one who responsible for radio equipment, and the one who responsible for all another equipment on board immediately. And it's something like flying engineer. So 5% in this airplane, 5 in crew, they are flight crew, and we need to add stewards there also. Here is immediately given in internet that for Antonov we have pilot, co-pilot, and three stewards that approximately correspond to the norm that I said, 80 people, 3 stewards, practically 1 to 25. And when it comes about Airbus, it depends on what is inside. It's given in internet that it depends on what cabins are inside, and for different of composing, let's say, of these cabins, depending on the company that buy airplane. So let's imagine that we use the same norm, the 25 people, one steward. That's it. It's enough already to start calculations. What our calculations are? We need to calculate relative masses for collected data. You will collect no less than 5 airplanes, please. I show you only 3 airplanes, but you see the table was prepared for 5 airplanes. So 5, 6 airplanes, please no less than 5. No, if it's difficult for you, 5 it's enough. If you might find more like 5, 7, it's not for me, it's for you. You understand? It will be better. What additional information you need to work with in this data that you are collecting? You also need to work with geometry, at least elementary things like area of wing, span, it means distance from the left tip of the wing to the right tip of the wing, and chord, and some geometrical data like, for instance, if it's swept wing, you need to see the angle of sweeptness. If it's type of engine, it's important. I'm not talking about particular name of the engine, type of engine. Additionally, you need to pay attention how airplane is composed. Is it low wing or high wing? Is it stabilizer T-shaped, stabilizer of so-called low position joined to the fuselage? Next, not only type of engine, but where engines are. Variants of engines placing, they may be very different for passenger airplanes, especially. It may be on the wing, on the wing. It may be at the end of the fuselage, like behind of the passenger cabin, on the rear portion of fuselage. So here should be additional column, something like short description of the airplane. Again, it's not for me, it's for you, because next you need to compose your very own airplane. And the most difficult questions for you will start when you try to arrange this general view to join all the things that you have been calculated and chosen in parameters, and now it's necessary to combine them all together. Then you will have a lot of questions. So better to save the picture of prototype, some short little picture of prototype also for yourself and in your reports. So your reports will look approximately like this. You already understand. First, you have some data that you have collected here, some at least like this, as I said, at least. If it will be table with a little bit more columns, it's okay. It will be maybe even better for you. Here is we have this characteristic which is necessary for us. The cruise speed, I wrote it in Mach number, but you understand that it's maybe recalculated to their kilometers per hour or 2 meters per second, as we need in calculations. Also, be please attentive what system of units you use. I insist on metric system of units, on international system, no pounds or yards or something like this, please, or foots. Give everything in normal metric system: kilograms, tons, meters, so on. And as I already said, we are going to use formula of Możайski and to use step 1 to use I'm as lazy person. Actually, any engineer it's supposed to be lazy, because while engineer on his leisure, engineer actually thinks. The engineer who hurrying too much first will work and next will check mistakes and work with mistakes, let's say, and it will be much longer if you still first you are thinking and next you are working, and thinking to working for engineers usually like 3-1. So as I already said you, and one more important moment, when we are working by hands, we may do mistakes. So excluding human factor, while calculating, while making decisions, while manufacturing, it means increasing the accuracy, usually accuracy of whatever, of calculating, of manufacturing. Look, I copied the same data to the that one I need to delete. I copied the same data to another program, to Excel, electronic tables. I trust you use something like this, or you may use calculator, no problem. And what is first you see, here is takeoff weight. Next, empty airplane, empty equipped, more probably, as we agreed with you. Next, the same, look, amount of cargo, of people in the crew. Now it's necessary to recalculate this amount. We don't need amount, we need what? We need weight, because we are going to work with weights. And as I wrote everything here in tons, I recalculated also in tons. What do you see, like 0.48? Quite clear, you understand. It comes about 2 people I took flight crew, 4 stewards, altogether 6 people. 6 people by 80 kilograms. It means that their general weight is common weight is 480 kilograms, so it's 0.48 tons. The same for Antonov 148. Here is 400 kilograms, and the same is for approximately the same for Tupolev 104. 5-person flight crew and plus stewards. Altogether, you see the weight of the crew in tons. Next, it was payload also in tons, for payload, once again, consideration is one passenger is 80 kilograms plus 40 kilograms of luggage. After this, we see, no, here is, you see it practically what I did, 107 to 0.12, and for each place is like this. And finally, we have fuel. What next? Next, we need to calculate the relative weights. Those relative weights are, look, the relative weight of structure plus equipment. That one divide to maximum weight, to take off weight. Approximately, you see, structure plus equipment for this airplane, it's approximately 0. Almost 60%, but not 60% really. Let's repeat it for another airplanes. And what do we see? Approximately the same values, but they a little bit differ, of course. Why? Because these airplanes not completely here is wrong. Here is 3000. I said I checked everything. No, it's around 3000. Let me check it again in internet. They a little bit distance in range. Of course, when you collecting the data, you should be more accurate in order to reduce your problems with this analyzing of statistical data. And that one is jumping out of the line, let's say, because this one is for it's very old. No, like it was designed with using of another traditions of design, then it's another kinds of materials and so on. So everything may affect all the final result. It's rather also short range. No, it's so-called middle range, around 3000, as I'd like Antonov and Tupolev. But you see difference in weight of structure is significant. Old one, it's like more heavy, no, relatively heavy with respect to the new one, because new one designed already in another technical level of design, and we have already another materials, including composite materials and so on. And A318, it's just with another range of operating actually. So when collecting the data, of course, try to preserve plus minus 10%, no more, dispersion of passenger and the range values in order to reduce your problems, as I said. Next, after we repeating the same practically for each place, let me to show you quickly. I will try to. Each time I divide it to the first column, you see. It's about crew. It's less than percent in each case. I left this for purpose, this face, the first, no, this is empty line I left for purpose. In order you see that here it's supposed to be Bombardier. Так, let's move it down. For closer correspondence, let's say, to what we do. No, I hope anyway you understand what is it. It's convenient, of course, not to have this window permanently interrupting. Sorry. Next, what is next? The weight of payload, relative weight of payload. Ой. Ой. Да что ж такое? А вот не надо было трогать руками, называется. Okay, let it be. System decided to help me, you see. No, at least now we see exactly in front of the airplane we need. Так, equal to payload divided to takeoff weight. Great. Empty place equal to fuel divided onto takeoff weight. So using calculator, I will have the same, but I need to copy values. No? So I use it as big calculator. You understood? Well, and actually now it's my turn. After I did it, of course, we may, have problems because I'm awkward. Of course, we may do something like average, but it will be not ideal way to solve it. As I already said, because we have 3 different airplanes. Now, let's imagine that we are working with airplane like this one, that one, and this one outstanding because it's less. No? And approximately it comes about 0.55. Next iterations of design, as I already said you, it will be changed. The weight of real structure will be different, but approximately, let's imagine that we have 0.55. Here is the crew. You see, each time crew is practically 1%. What this 0.007, it's less than 1%. For simplicity, I may write right now, decide right now, 1%. Next, it's payload. Payload, it's around 20% in the new airplanes. Do pay attention. Almost 20%. Here is almost 20%. In old one, 12. Why? As I already said you, it was old one. And for the same range, it will use more heavy engine because engines been not so perfect as now. For the same range, it will use more fuel again because engines less perfect, they eat more fuel than considering even the same type of the engine. And so on. There are a lot of reasons, and this one it's like outstanding by some values because it's the old one. So when we're collecting statistical data, better to use more modern airplanes, modern models of airplanes, not like of 50 or 70 years of previous century. That is why I left it here in order to show you this effect, actually. Let's imagine that we are working with new materials, with new engines, and so on. So payload is around 20%, and weight of fuel 22, 25. Now it's our turn to make our decision. Here we need to fill, of course, this table, to copy this data. Do permit me, I will not do it in front of you once again in order not to waste time. Our decision. Step number 2. For the airplane that we are designing, let's decide what will be our first distribution of weight. As I already said, let it be relative weight of empty airplane 0.55. 55% of the whole airplane consists of structure, equipment, chairs, toilets, kitchens, and so on. Payload, only 1/5 of airplane, and maybe it will be less after, maybe even after we calculate it, maybe it's appears that the airplane will be or lighter or heavier, and payload relative mass will be changed. Right now think that it will be 0.20, 20%. Fuel for appropriate range, let's think it's 0.25. In case range of airplane is longer, in this case, relative weight of fuel, relative mass of fuel will be greater. And if relative weight of fuel is greater, it means that here we need to think over something about the mass of the airplane, relative mass of the airplane, relative mass of payload, and so on. So relative mass of fuel, in this case, 0.25. Crew is 1%, 20, 25, and I hope you already have noticed it. Some important problem. What is important problem, people? Now I have 101%. Yes? Altogether, it should be approximately, not approximately, but exact value 1. But right now I have 1.01, 101%. And in order to change the situation, I should do either like this, and in this case it will be 100%, or I may leave here 55, but I need to change this, and so on. Now, of course, it's only first iteration. At the first iteration, it's not so dreadful problem, but even first iteration already may help you to see what you need to pay attention for, let's say, in the future designing. Okay, so what is the value that we certainly know out of these relative values? What we certainly know? We know absolute value of payload. And we understand that if absolute value of payload, here it's shown for you, no? If absolute value of payload is 12 tons, because we have 100 passengers, and each of them weighing with luggage 120 kilograms. So 12 tons, and these 12 tons are, according to our decision, is 1/5 of the airplane gross weight. So all the airplane supposed to be 400 of person, 60 tons. And that is our zero weight we are starting with in order to continue with geometry of airplane. By the word, let's compare to airplane weight in your statistical data. Once again, remind you that one it's for less amount of people, like 3/4, not 3/4, but 4/5 of 100. And this value, actually, we should add here around 20%. Let's check by the word. Calculator has disappeared. Was opened preliminary, has disappeared. Traitor. 43 and 7 divide to 4, multiply on 5. 54 is less. Now, then we already have selected for the zero weight. What about Airbus? Airbus for 100 of people. No, there is not 100 of people. It's around 107 for this takeoff weight. It's a little bit more than 60 ton. Let's try to recalculate. No, it's like for 1% here should be done. I'm afraid I'll do mistake here. 10% out of this, it will be 6. Да? No, approximately 60. For if you recalculate, if you create proportion with decisions that I already made instead of you, do forgive me here. It's just example. 100 of people 60 ton, and here is 107 of people 68 ton. If you recalculate it, it will be approximately a similar value. Sorry. So let's stop on this. Zero weight for us 60 tons. What is the next step? Next step, geometry of airplane. We need to create wing now. First, what does it mean create wing? First, we need to select the shape of the wing. How to select shape of the wing? Here I place it some pictures of airplane. Actually, these pictures, they are not to show the shape of the wing. These pictures to explanation how to calculate the area of the wing. Do pay attention that area of the wing, consider it like left and right half of the wing, plus the center wing. That is taken by the fuselage, it doesn't matter. It's considered like belonged to the wing area. So area of the wing is distance from left tip to the right tip multiplied on chord, so-called. But certainly chord may be different. You see the value of chord, root chord is very great, and here is very little value. How to calculate this? Here, tapered wing, how to calculate this? Half elliptical wing, swept wing, how to calculate? And in this case, we have so-called relative parameters. Relative parameters, we have wing aspect ratio. No, that is, you understand, how to calculate it. And how to calculate area at all. No, once again, to calculate area, we might recollect this. We have to recollect this. Forces acting to the airplane. Now, of course, right now you see the plane in horizontal cruise flight, and quite clear that forces that acting while takeoff and landing, they are greater. I hope you do remember. So while calculating, we should be accurate with these values. We will try to do it together to see what we might have finally. And the formula that should help us, formula of Zhukovsky. No, you do remember this formula, which is called in English literature formula of Newton, and in our literature is called formula of Zhukovsky. The simplified formula for calculating of some parameters. What is in this formula? Speed, but it doesn't help you to understand the cruise speed. Next, you will see what will be the problem. We need to understand cruise speed. Yes, of course, we need to understand cruise speed. But also we should remember that in cruise flight, speed much more. And it means that lift may appear and be sufficient for flight with less wing. But on takeoff and landing, when you have low speed, I checked it for Antonov 140 and it's appeared 120 kilometers, no, 120 kilometers for the moment of takeoff from runway, exactly. But in flight, it has speed around 900 or 800 kilometers, 4 times more. So if we take into consideration the speed of cruise flight, here we will have value of wing at least 4-5 times less than real one. Next, in cruise flight, lift equal to the weight. But in order to make airplane take off and take heights, it's necessary to have lift sometimes more. What does it mean sometimes more for you? You are not fighters, you do remember, please. So you should not take it 5 times more, 3 times more. It's too much. For passenger or cargo airplane, it will be too much. But at least something like 1.2 with respect to the normal cruise flight, or 1.3, like 30% of overload. People sitting in armchairs in passenger cabin, they will feel their own weight heavier for 30%. It's already even too much. So here we need to remember about this simple rule that lift equal to the weight. But actually, for calculating even the very first calculating of area of wing, we will use little bit greater value of lift. Theoretically, takeoff mass for our 100 passenger 60 tons, so lift is 50 tons, enough, but only in cruise speed, in cruise flight, you understand that. One more parameter is density of air. What is the density of air? Find it in internet and you will see value. This one, 122.5 kilogram per meter square near the ground. But we do remember that we have so-called standard atmosphere, and these standard atmosphere parameters show that With heights, with increasing the altitude, air properties change. They change and they vary from what we have on the ground. Here I show you, to remind you, they are so-called relative parameters. What here is in the corner visible, that relative parameters of density, pressure, and temperature, given with different colors. And our line is of red color. Now let's see. When altitude, and it's given in percents, of course, from 0 to 1. When altitude is 0, we have standard atmosphere parameter, this one. When it comes about the cruise flight, let it be 800 kilometers. Red line show approximately 0.4. 0.4, it means it will be 40% only of this density. That is also necessary to take into account. But once again, we will take into account different variants, cruise flight, and there will be another speed and another density. Take off landing case, and it's near the ground and with much less speed. Well, no, here it's written what I have already said you. How to recalculate it? No, there is no difficulty. No any difficulties. Very well. What is next parameter? Next parameter is this one, CY, coefficient of lift. What is wrong with this parameter? Let me to remind you what is wrong with this parameter. It depends on angle of attack first. Not even like this. First, it depends on profile. What is the shape of profile? We don't know. Also, it depends on the angle of attack. What is the angle of attack for your profile? In cruise flight, in takeoff, in landing? We don't know. So we know nothing, you understand it. We know nothing practically during all these calculations, we know nothing. And we may do it only approximately. Here you see reminding for you how this lift coefficient depends on the shape of the wing. Red one for the straight wing, and the blue one is for swept wing. Swept wing is more typical, once again remind you, it's more typical for airplanes flying with higher speed. What idea of such a wing? I hope you do remember. When we flying already with transonic speed, wing still fly with subsonic speed and has less drag. Next, no, here is practically about the same. This coefficient depends on profile, I said. How we may, no, first we may took different profiles for our airplane. And secondly, we may change the shape of profile. Here is angle of attack, reminding you how it's affect to the lift. And we may change curvature, let's say, of our profile while flying due to changing of flight controls position, so-called high lift devices position. And what I placed these diagrams for, of course, it's not real one. No, in terms that it's not for your airplane, but at least it may give you some idea about ranges of those values. Typically, it's considered that non-flexible wing made of metal, I mean, for modern passenger airplane with rather big payload, rather big, it means it comes about more than one passenger at least. Wings are significantly stiffer and made of metal usually, so or composite materials in modern conditions, and they are considered like non-flexible wings. For non-flexible wings in cruise flight, it's around 1. Also with variations, but when it comes about takeoff landing and you are using high lift devices, it's maybe 0.6 up to 2, or even a bit greater. How to understand which one will be in real? In real, let's come back to the slides that we have already opened today once. And you see this scared face, it's like tracing us permanently. It's follow us. Let me to remind you what you have seen, what we talked about, how to determine characteristics. Like this. Wait, like this. Wind tunnels. We have different profiles. We use wind tunnels, special laboratories to determine these characteristics. So when you have already a real airplane, you may do wind tunnel tests. In wind tunnel tests, either you may do separate testing of some different elements like wing, stabilizer, so on, for this profile, for this not even span, but wing aspect ratio. You do remember the ratio between span of the wing and chord of the wing. Wing is relatively long or wing is relatively short. It's important. It's important for drag. It's important for lift. It's important. We do remember this. So this characteristic may be determined in case you're able to do model. But to do model, you need to know geometry. And we came back again to the same circle. We don't know geometry yet. We don't know sizes. We can't esteem properly the value of this coefficient of lift. So we take it some average value approximately for the first calculation. Let it be 1, for instance. Let it be 1 for our very first calculation of this. And once again, come back to the formula. So we already know everything. Look, lift, it should be 60 tons, but we have agreed that we take at least 20% more because we are talking about take off. Next, CY, no, let it be 1. No, at the take off landing, it will be even more. Density of air, depending where we are, near the ground or on heights, and speed. For primary calculations, of course, we are forced to use those speeds that are less. I mean, we need to use speeds during takeoff and landing because they are sometimes less than speeds of cruise flight. And let's try to calculate all together. Calculator is open. My notebook is ready. Let's repeat these dreadful calculations. Maybe better even to use Paint in order not to spoil slides additionally. We will use Paint and calculator. Lift equal to CY, coefficient of lift, density, speed in square by 2, and here is we have unknown value. Unknown value is area of the wing, what is in question. How to determine this unknown value? No, quite clear that to determine this, we need to divide lift to this beautiful formula, practically, completely, like this. And after the ultimate simplification, it looks like 2 lifts divided onto CY, density, and square in square velocity, square speed. Very well. To start, let's analyze what we already know. Let's rewrite it now in the values. Lift. Lift supposed to be, no, 2 lifts, according to what we did here. It's supposed to be 60 tons. Don't forget to rewrite it into kilograms, please. 60,000 of kilograms. And considering that on takeoff and landing, we need to have it a bit more, let it be like this. Coefficient. No, now we're talking about near the ground on takeoff. Let's think that we are talking about coefficient. Let it be even 1.5 because we use high lift devices. Next, density of air. Watching the units. Density of air, weight was given 1225. Here is, да? Вот, 1225 kilograms per meter cubic. It's okay. 1225. And finally, the speed. Speed is, no, I'm already said you, speed supposed to be given in so-called technical task after it was after it was customer demand to you. You developing the concept. We discussed this in one of the classes. I hope you do remember. You propose so-called analyzing conceptual projects like what is the concept of your general appearance of the airplane that you propose to design. And next, designers compose so-called technical specification, technical task of the airplane. We are given some ultimate parameters of this airplane. And one of the parameters we should follow too, maybe because we also analyze statistic, for instance, the speed of takeoff and speed of landing. Have repeated already maybe dozen of times today that they are significantly less than cruise speed. So if we open internet, let's even do it right now to prove my words. I did it for Antonov. On 1/4 speed of takeoff. No, I did it in my language, so not sure that it works the same in English. No, I hope it will. Takeoff speed, not Thank you. It doesn't. It gives another value now. in my language, it give another. It gave me another value. In English, it's show you see. Да? It show 240 kilometers per hour. Okay, let's take 240, for instance. In contrary to the speed of cruise flight, that was more than 8 kilometers per hour. But once again, we need everything in the same metric units. Kilometers per hour, it's not metric units. So what we need to do? First, we need to recalculate the speed. Or here we need to write it correctly. What does it mean to recalculate the speed? Let it be 240 even, as it's given there. But it's 240 kilometers per hour. Let's recalculate it to seconds. We're working with seconds. And how many seconds we have? No, you do remember. We have 60 hours, 60 minutes. So altogether, easy peasy, we did it. Here is, okay. Divide on, you see, it's around, great value. 66 and 6 in period, let it be 66.7. 66.7 square. So simple. Is it really so simple to calculate the area of the wing? Let's calculate. Once again, remind you, not so simple, because next it's appeared that it's a bit wrong. Wait a second. So we have, no, first, do forgive me, first I will, in order not to use brackets and so on, if you'd like, we may do it with brackets and squares and like the whole formula, but more simple will be for me to do it like this. 66.7. Great. Where I'm typing enter. 66.7 square, multiplying on 1,2,2,2,5, multiplying on 1.5, and has got some value. Let's copy this value. And now we need to divide 2 multiplied on 1.2 multiplied on 60,000 60 tons of kilogram, 60 tons, 60,000 of kilograms, and divided on the values that we have calculated preliminary. 70 square meters. Look, 17 meters square. Can't be. It's practically without wing, you see? And if we change some parameters, for instance, let's imagine that here less speed, which suppose maybe I should ask not takeoff speed, but landing speed. Wait a second, once again. Ay. Do work, please. Speed of landing. No, it shows the same value. Fantastic. Okay, but once again, it's not realistic value, and so we may check, not check, we may play with this, see no point to continue this game. Actually, if we repeat what did I said, but with another speed, no, look, for instance, 120 kilometers per hour, as it was given in information that I've seen before. And by the word, we may use, of course, different airplanes for this, yes? Let's try to see how it's changed. The more slow airplane on takeoff and landing, it depends on the engine. It depends on the how it was designed. It depends on a lot of factors actually, and finally it will be understood only after flight test. Whatever we have calculated, next it's supposed to be checked and доказать, proven by flight test. Now, once again, considering that we have less takeoff speed, 120 kilometers in meters like this, divided in order we see what is it in meters per second, 33.3, let it be, no? And now 33.3 on. Next, the air near the ground. Next, let's think that we have less effective takeoff devices, high lift devices. So it's not 1.5, but let it be 1, for instance. And in this case, what we have, copy. Let's try to see what we will have now. 2 on 1.2 on 60 tons, divide. And now you see it's completely another area. Look, and it's not linear dependence. Do pay attention. Now we has got this one. We change it, takeoff landing speed twice, and look what happened. Area changed, not twice. Area changed practically 5 times. You see, 5 and more times. Well, no, we may check some cases, may consider some different variants that we have or not have some high-lift devices that we are working with another speed and so on. Not reliable way, seems like, no? Formula of Zhukovsky may help us to esteem something right now. But as we have already very rich experience of another engineers, where is this rich experience? Where it's hidden? This rich experience is here in statistical data that we have collected. They already proven their decisions. They already fly. And here we have their wings areas, and we know their takeoff. And understanding that approximately we are going to use airplane of the same class, And it means that so-called design scheme of airplane, I hope you do remember what we've been talking about, structures, this structural design scheme, whether it's of truss type inside or it's of beam type inside. Let me to jump again to the bottom of slides. What here is approximately that what you see right now, it's our Antonov 140. It's approximately the same will be for another airplane of this class. Of course, it's not ideally the same in sizes. Of course, it's not the same engine, of course, so on. But approximately, it's the same story inside. You have beam-like structure because you're working with rather heavy airplanes of higher speed. For modern passenger and cargo airplanes, typically it's not longeron structure, not spar-like structure, but it's so-called, forgot the word in English, torsion box. In our language, it's called caisson. And maybe because it came from French. This torsion box structure, it means that you have rather thick skin made of metal, quite clear, supported with stringers, and this skin with stringers together help to spars to work to resist the bending moment. It's something like half to the half, approximately half of all the loads due to bending moments will be taken by spars, and around half will be taken with these so-called working skins or working panels, well, approximately. If it comes about low-speed airplanes, in this case, spar more loaded with respect to the skin. In this case, spar take practically 90% of the all the bending moments. If skin made of fabric, of paper, in this case, spar completely working for 100% of bending moment. And if we understand approximately that we follow to the same inner structure and distribution of work between inner structure elements, we are going to follow to this design. Because in other aircraft designers, they already proven this work. For that or another type of design, I said that, if you remember, typical values of so-called specific load for the wing are known. What I left here in slides earlier, sorry, the table with, for instance, not that one maybe, да? With something like this. Wing loading, depending on cruise speed, here is, it's given. It's so-called specific wing load, depending on how quick your airplane is. And you see these values are, no, here is it started, the lowest speed is started from the least airplane, the closest to the zero. It's around 100 kilograms per square meter. No, it's not given here, but we will calculate it next. Kilogram per for square meter of the wing. It's so-called specific load to the wing. It's practically the lift which is like taken, received by 1 square meter of either lift or weight or whatsoever, some load which work with 1 square meter of your wing. And the higher speed of airplane, the higher these loads. Why? Just because they use another inner structures design, which more appropriate for loading for that or another way. And also materials are important, as I said you already. If we compare it with the old variants of airplanes, of course, the specific load will be less for the wing because we had no such perfect materials like we have now. And if you compare it with airplanes of the last generations, like 20 years, not far, then specific loads will be higher in the same class of the airplane. As we do not understand how to choose it here, for instance, no, like we are not experienced it yet, we may at least compare it by statistical data. We have takeoff and we have area of wing, and that we are going to do right now. Here is explanation to the same plot, as you see. No? They analyzing the aspect ratio of wing, it's so-called relative elongation, let's say, no? For different airplanes, it's been shown here. They show different parameters of the wing, like chords in feet, area in square feet. No, remember that I ask you to use metric system. And they analyze next what wing loading. No, do forgive me, it's not next because I scroll it up to you. Sorry. No, at least you may see that for different airplanes, they show maximum takeoff weight in kilograms, wing area in meters square, and they show wing loading. Do pay attention how much vary these values in this table and in that plot, as you might see. And do remember why? Because it comes about of airplanes of very different classes. No, this to compare this Beach Baron airplane, Beach Baron, Beach Baron, Beach Baron. I approximately know what it looks like. Let's see together. Beach Baron airplane. I hope I have practical hasn't done mistake. What you see? It's flying cab. It's very little airplane, да? And what it's compared in line with, like Airbus A380, Boeing 747, and so on. Of course, they are not comparable. You understand it. No, in terms of their wing loadings, they are not comparable because this one is comparatively low and comparatively little with those airplanes. And quite clear, its inner structure differs significantly, and all the decisions, approach to design of this little structure is much vary. Maybe it's some elements inside the fuselage, they does not exist like beam elements. They maybe it's something like truss covered with unworking skin, you know, like eggshell around, which doesn't work. It just cover creates the shape. That's it. So please let's use such parameter, but use it only for your own class of the airplane. And right now we are going to do it where we have been here. Yeah? One more option to check your decision. It's by wing specific load. It's just to remind you that it's necessary. I forgot to switch off these signs. Maybe they irritate you. I'm blind without these signs, as I said you in Word. But maybe it's not useful for you. Let's see. And let's use calculator once again. I'm already did it. I know the values, but let's see together. Look, area of the wing of Airbus 122. Let's take it less in order it does not jump permanently. 120, or in contrary, do forgive me. We are calculating weight, maximum takeoff weight to the area. 68 tons to the 122.7 meters square. 554, you see. Just remember this value. Antonov, 43.7. 43 kilograms in kilograms to the meter square. They are 87,500, almost the same value. No, comparatively to 100 and 500, almost the same value. No, and Tupolev, of course, will be more heavier, I'm afraid. No, I mean, it will have less value of in kilograms to the 1 meter square. Why? I'm already said you. Even considering that this airplane of the same class of range, of speed, and so on, it was made more than 60 years ago, and it means that they been working with another materials, and they've been working yet with another experience, with another technical experience. They have no experience of creating of airplanes like we have it now. No, anyway, we will see it. 74.5 in kilograms divided to area of the wing. Much less comparatively to those two, which were 550 and 500. That one is almost 20% less. So if we analyze our class of airplane, disappear please, you may do it approximately using such data like you see here. I mean loading of the wing. No? That if your airplane is around similar to one of those, you may take value here, for instance, or approximate value here. Or you may use it out of your statistical data that you take immediately. This face is never, it's my love. Da. And you may use statistical data to understand what is area of your wing supposed to be. First, we determine specific value of load. Let it be 500. Like it's not so high like we seen in Airbus. Let it be 500. 500, it's not much. And what we will have, oh, sorry, we're already lower, maybe, no? What it will equal to. Now we have 60-ton weight that we have stopped on for 400 of passenger. We have decided our airplane in zero approach should be in zero iteration. It should be 60 tons. 60 tons divide onto 500 to understand 500 kilograms per square meter, the specific load, to understand what's supposed to be wing area. Value is 120, and let's compare to what we have in another airplanes that we have seen in statistical data. Once again, remind you, we're supposed to compare it above the all with Airbus. No, practically, you see, it's the same. Why not with this one? Because it's less in passengers. I collected data not accurately. No, I'm already said you have made it on purpose. I did it on purpose in order to show you typical problems that appear in this case. And quite clear, it's very different from the ancient variant of the passenger airplane of the same class. On this moment, we will do interruption in record, and after interruption, I will continue, and you will see continuation. So first, I hope you understood what we work with. Do forgive me that I scroll it in the wrong place. It's because in another slide. First, to esteem new designed airplane, we need to collect statistical data, considering that we know only what is our payload and what is the range. Now, approximately, we may take information from our customer of what speed of flight they prefer, or maybe they don't know it. Maybe it will be your choice next. And we collecting information about weight, geometry, some composition scheme of another airplanes of the same class, approximately for the same amount of passenger or same amount of payload, and approximately for the same range. And starting with recalculating relative parameters. First, we recalculating the masses of airplane, future airplane, finally deciding what they will be for our new airplanes that we create, checking that our masses equal to 1, relative masses equal to 1, and next understanding that out of our relative masses, 1 we may compare with absolute mass with payload. We may determine what's supposed to be zero iteration weight of our airplane. We did it. And next, for this zero iteration weight, Considering the elementary things about balancing of forces in flight, during takeoff, during landing, we are trying to determine some parameters of aircraft geometry. And above the all, of course, we are working with the wing. Let's interrupt on this, please.